Welcome back to my channel. If you are new here, I like to introduce myself. I am Jumana Khanfar, a teacher at Taqarub International Schools. Today's lesson is about Newton's laws of motion. We will study the first law, the second, and the third. Actually, you need to know them in order, because this is something standard. And we will discuss some different cases related to each of the laws. Newton's first law, also known as the law of inertia. An object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction. It means that this object will stay moving at constant velocity, because velocity is the speed with a given direction, unless acted upon by an unbalanced force. We discussed that before in the previous video. We said that for an object to move, there should be an unbalanced force. For example, if you have a book on your desk, this book will stay on the desk unless someone moves it. This book cannot move itself. It needs an external force to move it. Also, if you roll a marble over a very, very smooth surface, this marble will stay moving in the same direction and the same speed unless acted upon by a force to slow it down. If we assume that the floor is perfectly smooth, it means that it is frictionless. And this is not found in real life actually. The marble will never stop. But in real life, even if the floor appears to be very smooth, if you zoom in, you see some imperfections in the surface. So finally the marble will stop because of friction. A mathematical representation of Newton's first law is sigma F. Sigma means the vector sum of the forces, or the total force affecting an object, is equal to 0. Actually, we can apply this formula when the object is at static or dynamic equilibrium. The object is at static equilibrium when it is at rest, and it is at dynamic equilibrium when it's moving at constant velocity. Same speed and same direction all the time. So we can apply this formula when the object is at static or dynamic equilibrium. Now, before we solve some questions, let's go to Newton's second law because they are related to each other. Newton's second law states that the acceleration of an object is dependent upon two variables. The net force, which is sigma F, acting upon the object, and the mass of the object. A mathematical representation of this law is sigma F, the vector sum of the forces, is equal to m times a. A is the acceleration of the object, and the direction of the net force is same as the direction of the acceleration of an object. Okay, the acceleration could be positive or negative or 0. If the acceleration is 0, then we go back to Newton's first law. It means that the object is not speeding up or slowing down, so the object is at static or dynamic equilibrium. So this is Newton's first law. If the object is speeding up, the acceleration is positive. If the object is slowing down, then the acceleration is negative. If the object is speeding up, it means that the force, the net force, is in the same direction of the motion. If the object is slowing down, it means that the net force is in the opposite direction. To understand Newton's first law and second law, we need to solve some questions. A 5 kilograms mass is pulled to the left along a smooth horizontal surface. When the surface is smooth, we assume that there is no friction by a string, so there is tension in the string. The string has a tension of 20 newtons. T is 20. Determine the acceleration of the mass. The net force is to the left, so the acceleration will be to the left too. We assume that the direction of motion is the positive direction. The first step to solve a such question is to construct the free body diagram of this object. Fg down, Fn up, the tension to the left, and the friction is 0. We said that in real life there is no zero friction, or there is no 100% smooth surface, but we assume that it is 0 because the surface is smooth, so it's negligible. So the friction here is 0. Let's apply the formula. Here the object is moving, it's not at rest, so we can apply Newton's second law. Sigma F equals ma. We can apply this along the x-axis and along the y-axis. The sum of the horizontal forces and the sum of the vertical forces. In the x direction, we have t minus 0. T is 20. 20 minus 0 is 20 equals 5a divided by 5 by 5. So the acceleration is 4 meters per second squared to the left because the net force is to the left. If we need to find the normal force, we can apply the same formula in the vertical direction. Sigma F equals 0 here in the vertical direction because the object is not moving up or down. It is moving over a horizontal surface. So sigma F here is Fn minus Fg. This is 0. So Fn equals Fg, which is 50, because Fg is the mass times g times 10 newtons. Let's take another example with more details. A 10 kilograms mass is pulled to the right along a rough horizontal surface. So there's friction here by a string tension. The string has a tension of 20 newtons, so this is 20. Determine the acceleration of the mass. Again, we need to find A. If the coefficient of kinetic friction between the mass and the surface is 0.1, this is mu that we talked about before in the previous video. It is the coefficient of friction between the mass and the surface. It determines the roughness of the surface. Okay, firstly, let's construct the free body diagram of this object. We have 20 newtons to the right, the tension. The friction is to the left. Fn is up. And Fg is down. Because there is no movement in the vertical direction, Fn and Fg are equal. So Fg here is 100, 10 times g. Therefore, Fn will be also 100. Now again, sigma F equals ma in the horizontal direction. Sigma F in the horizontal direction is 20 minus the friction. This is equal to the mass 10 times A. We need to find A, so we have to calculate the friction. Friction is equal to mu times Fn according to the previous formula. Mu is 0.1, Fn is 100, so this is 10 newtons. 20 minus 10 equals 10a. 10 equals 10a. Then the acceleration is 1 meters per second squared to the right because the net force is to the right because the tension is more than the friction. Okay. Let's take another example when the force is applied with an angle. A mass m is pulled along a horizontal surface by force F, as shown above, if the resulting motion is constant velocity. It means that sigma F is 0 in both directions, x and y. Then the frictional force is equal to, let's firstly construct the free body diagram. This is F with an angle of theta. Let's decompose this force to two force vectors, F cosine theta and F sine theta. Also we have Fg down and Fn up, and the friction to the left in the opposite direction. Now let's redraw this without this force because we already decomposed it. We have these forces, F cosine theta, F sine theta, and we have Fn up. Here to the left we have the friction, and down we have Fg. If the object is not moving, or if it's moving at constant velocity, I mean when the object is at equilibrium, the net force in the x direction is 0 and the net force in the y direction is 0. Then the frictional force will be equal to F cosine theta because they cancel out each other. So the answer is D. Okay, now what about the normal force? The normal force plus F sine theta, these forces are equal to gravity because they cancel out each other. So Fn is equal to Fg, which is m times g, minus F sine theta. Okay. We need to focus now. We have an inclined plane, so the configuration of the forces will be different. A 5 kilogram mass is positioned on a 30 degrees incline, so the angle here is 30 degrees. It is kept stationary, then the net force is 0. By a string pulling parallel to the incline, so this is the string here, determine the tension in the string. Okay, let's construct the free body diagram. Tension up. Fg is always downward and Fn is perpendicular to the surface. All the forces are either perpendicular or parallel to the surface except Fg. To be able to analyze this problem, we need to decompose the gravity. This is 30 degrees here, and this angle is also 30 degrees. So here, this is Fg cosine 30, and this is Fg sine 30. Okay, determine the tension in the string. If the object is at rest or stationary as it is mentioned here, then the net force is 0. So tension equals Fg sine theta and Fn equals Fg cosine theta. Then the tension is Fg sine theta. Fg is mass times g, sine 30. Sine 30 is half, the mass is 5, and g is 10, approximately 10. 50 times half is 25 newtons. Now let's go to the third law. Newton's third law states that for every action there is an equal and opposite reaction. Suppose that you are standing on a boat. If you and the boat are at rest, the net force is 0 and you are not moving, your velocity is 0. If you step out of the boat, so you move to the right, what do you think? What will happen to the boat? It will move a little bit backward with a speed less than yours because you are lighter than the boat. This is an application of Newton's third law. Also, we can walk because of Newton's third law. When you walk, you push the floor backward, so the floor as a response pushes you forward with a force that leads to motion, to your motion. If you have more examples of Newton's third law of motion, I'm interested to know. You can write them down. In the next video, we will discuss a more advanced case of Newton's first and second laws. It is the compound body problems, like the poly problems. Thanks for watching and see you next time.